Good morning, everybody.
Good morning, sir.
So I will just wait till a few more people join. Okay, so let me get started. Okay, so we are now going to start a new topic. So the topic is related to statistics. So this is the second half of the course. Even though it's the second half, there are not too many things that we are going to talk about here in this course. So you will learn statistics as part of when you learn machine learning, because machine learning is based on principles of statistics. So all the other details that are there, you will learn in your machine learning class. So today we are going to do some things in statistics, some topics in statistics. So we will begin with what is called as probabilistic inequalities. Okay, so this is what we will start with. And the first of this is called as Markov inequality. Okay, so yeah, so for this, what we require is a positive, let x be a positive random variable. Okay, so what that means is that x cannot take any value less than 0. So if it is continuous, let me draw here. If it is continuous, it will be something like this: fx of x. It will have a density, in the positive side somewhere like this. Okay, this could be the density. Everything here will be 0, and if it is a discrete one, the PMF, what it will do is that it will not have any mass in the negative side. Okay, so here, for example, this is example of a positive discrete probability. Okay, positive discrete random variable. This is x. Okay, so now what we are interested is in the tail probability. So let me tell what that means. So basically, if you look at some a, say let's say there is a here, you are interested in what is this probability or what is this probability. What is the chance that x takes a value greater than or equal to a? Okay, so this is called as a tail probability. Okay, so that's the idea. So let's try to derive the Markov inequality from whatever knowledge that we have here. Of course, you don't know what's a Markov inequality, but let me just do algebraically a sequence of steps, and then at the end of that, you will see the Markov inequality. Okay, so let's start. So we know that expectation of x is going to be, so let's do it for continuous. So it is 0 to infinity x fx dx. Okay, can somebody tell me why I have not taken from minus infinity to plus infinity?
X is a
Positive
positive random
variable.
variable.
Yeah, thank you. Yeah, just to see if I'm still connected. All right, thank you. So this is what it is. So now what we can do is that we can, this is an integration. So you can always split integration at points. So what we will do is we will split it into 0 to a plus a to infinity x f of x dx. Okay, I hope this step is easy for everybody to understand. Okay, now we know, so let me write the correct notation. We know that fx, okay, is a density, is a probability density function. So it has the property that fx is always greater than or equal to 0. All right. And we also know in this region, when I'm integrating from 0 to a and x is taking value 0 to a, this part is also positive, this part is also positive. So when you multiply, it's a positive thing. And when you integrate a positive function, you'll get a positive thing. So what I'm essentially saying is that this term has to be greater than or equal to 0. Okay, it has to be some positive number. So if I am taking expression like this, okay, and if I drop this, okay, so what can you say? What I'm trying to say is, you have on the left hand side e of x. On the right hand side, I just omit this and I just write a to infinity x f x dx. So there is some positive term that was missing. If that was there, we would have had an equality. Since that is not there, what is the inequality going to be? Which side is going to be bigger, left hand side or the right hand side?
Left hand side.
Yes, that's right. So this is going to be this. All right, because I dropped something which was positive. All right, positive, or it could be 0. The smallest value it could take would be 0, but still that's a non-negative number. So I can write it in this way. So, okay. So now I will do something else as well. What I will do is that when you have this second expression, this term x here, I will replace it with a. Okay, so what is that? What am I saying? So I will take, instead of x, I will replace all x by a. Okay, so this was an x. So x used to take value a. Okay, then a plus 1, a plus 2, any whole range of numbers greater than a. But instead of taking all those numbers which are actually bigger than a, I reduce this x to a. Okay, I'm doing again an approximation. Okay, x is going to take bigger values, but I'm going to bring it down to a. Okay, what that further does is that it further reduces the this inequality. So e of x is going to be less than or this, which is also going to be further less than or equal to a fx x dx. All right. So I hope this is also clear to everybody. And this expression, if you see, this is going to be equal to this itself is going to be equal to a times. So what is this? So if I integrate from a to infinity fx of x, what do I get? Yeah, somebody.
P of x greater than or equal to a.
Yeah. So we get the desired tail probability. We wanted this thing, right? You will understand why this is required little bit down the line when we are learning statistics a little bit more in detail. But for now, let us just work with the fact that we need to know the estimates for tail probability many times. All right. So that's what this comes. And now if I rearrange a little bit, what I will get is that px greater than or equal to a, okay, is going to be less than or equal to ex by a. Okay. Oops. So this is called as the Markov inequality. So what that says, see, if e of x is small, what happens? It implies that tail probabilities will be small, right? Can you see that? So you are saying the tail probability is upper bounded by e of x by a. If e of x reduces for some reason, okay, for a random variable e of x is very low, okay, for that particular random variable, the tail probability also will be lower and lower. All right. So that is kind of not surprising, right? So e of x represents the expectation of x represents the like a single number that entirely captures best the entire random variable. So if that number is lower, it must be the case that the random variable does not take higher values in some sense, right? So that is what this inequality is showing us. Okay, so this is the first inequality, which is called as a Markov inequality. Okay, so I hope this was clear to everybody. So let's now talk about the next one. So that's called as the Chebyshev's inequality. Okay, so there was one problem with Markov inequality. What was the problem? It only applies to positive random variables. Okay, but we might be interested in things which are not necessarily positive, but have like a extended range. So something, let's say this is one. Let's say this is a density. Let's call this as fx of x. Okay, let's say this is the mean. Something. Okay, so this is the mean. What I may be interested is like around the mean symmetrically. Okay, so this is, let's say, mu minus a. This is mu plus a. I may be interested in not just the tail probability. I will be interested in like some distance away from mean. What is the tail? Okay, so this is also the tail, but a tail on both sides. Okay, this is the two-sided tail. Okay, so I will be interested in what is the probability that x, okay, the random variable x takes a value greater than, okay, greater than, so I mean to say what's the probability that, yeah, so x is, so yeah, so x is between mu minus a less than x less than mu plus a. So this is this inside probability. So let me just indicate that. Okay, so this is this probability. Okay. So this is this, but so another way to write this, if you observe, this is to say x minus mu is less than a. Okay, so this red region can also be written as x minus mu is less than a. Is that okay? Just observe this. So if there is a value somewhere here, okay, so suppose this is the value x. Okay, x minus mu, if I do, what am I going to get? It is going to be a number between minus a and plus a. And since I'm taking a modulus, that number will be strictly less than a. Okay. And if I want to if I'm interested in the tail probability, what that actually in turn captures is x minus mu is greater than or equal to a. Is this clear to everybody? How this is capturing the tail probability? This is the two-sided tail. Let me repeat. So Chebyshev inequality is for the more general case, okay, where your x need not be a non-negative random variable or a positive random variable. Okay, so Chebyshev inequality is for the general case, and here is an example of fx of x, the density of a random variable x. So I have drawn here. Okay, and suppose this is the mean mu. Okay, so since this is a not a like positive random variable or a non-negative random variable, what I'm interested when I say tail is some distance away from the mean. I should be talking of distances away from the mean. So for instance, this area here and this area here. Okay, let me not write with the same color. So you have to talk about some distances away from the mean. Okay, so suppose if I talk about this shaded region, I want to know what's the probability of that region. Okay, to arrive at that, what we did is we first understood what it means to be within the close to the mean. So that is this. Okay, that can be alternatively written as this modulus expression. Okay, because if there is a value here, okay, suppose this x is here. Okay, so x is here. Then if I do x minus mu, it will be a number which is between minus a and a. So with the modulus, it will be strictly less than a. So the two-sided tail probability is actually this. Okay. So now using this, now we understand this is the two-sided tail probability. And if you want to try to get a bound or a inequality or some kind of a control on this, what we need to do is we have to get some inequality with this. And to do that, we observe the first thing. So I'm saying this is also equal to the probability that x minus mu whole square is greater than or equal to a square. What I did is I squared on the both sides. Okay. So that doesn't change anything. Is that all right? Okay. Now what I'm going to do is I'm going to denote y as x minus mu whole square. So y is now the new random variable that I'm interested, where y is equal to x minus mu square. And what is the property of y? Can someone tell me what is the range values y will take?
Zero to infinity.
Yeah, y is going to be a non-negative random variable or a positive random variable. Okay, because you are squaring some numbers here. This squares will always give you positive things. So now, since we have already known how to do for a Markov inequality, we know how to do for a positive random variable. We can apply that same here. Okay, so now we know that this is going to be less than or equal to expected value of y. Y is nothing but x minus mu whole squared. Okay, divided by whatever comes here, right? See, ex by a. So that one we will write here. Okay. Now, what is that numerator? Can someone tell me what is this? This here, the numerator. What is that going to be? Have you seen this sometime? X minus mu whole squared. Expect. Yeah. So this is variance of x. So what essentially we have got is an expression which is saying this. So the two-sided tail probability is upper bounded by a function of the variance. Okay. So this is called as the Chebyshev's inequality. Are there any questions till here? Okay, very good. So let us now use this and try to see what type of results we will get. Okay, so let's take some examples. So let's first see an example of applying Markov inequality. So we know that. So let us take an example of x, which is exponential with parameter lambda. So first question, does Markov inequality apply here and why?
Yes, because x is greater than equal to 0.
Yeah, because it's an exponential, x is greater than or equal to 0. So let us first directly apply the Markov inequality. So if I wanted to say probability that x is greater than or equal to a, this is going to be less than expected value of x divided by a. So this is the Markov inequality. Okay. So what is expected value of so that means p of x greater than or equal to a. Expected value of this is 1 over lambda, right? So this is going to be 1 over lambda a. Okay, so this is the application of Markov inequality. So what is happening? The tail probability is reducing as a function of 1 over a. So it's the tail probability as per Markov inequality is going to 0. Okay, at what rate? At the rate of a inverse, right? So the larger and larger a value becomes, the faster it will go to 0. Okay. I mean, it will become smaller and smaller. The faster it will means I meant to say the rate is constant, but it will become faster in terms of the rate of a inverse. So let us try to do the same thing using the fact that we know x is exponential. So let us try to do that. So what is probability of x greater than a? So this is going to be directly using the exponential property is going to be a to infinity, okay, and lambda e power minus lambda x dx, okay. So let's try to integrate this. You will get lambda e power minus lambda x by minus lambda. I'm integrating between a to infinity. All right. So when I see the upper limit, it becomes 0. Okay. So if you just do it clearly, it will be e power minus lambda a. I will write it in another way. It is e power minus lambda into e power minus a. Okay. Sorry, e power minus lambda into, no, that's not what I wanted to say. It is e power minus some constant times a. Okay. So so now let it be, let me keep it as lambda only. Nothing, I didn't want to say anything significant. What I wanted to say is, if you use the property of x being exponential, okay, we can show that px greater than or equal to a goes to 0, okay, at the rate of e power minus a. Okay, it goes to at a rate much faster than a inverse. Isn't that right? Because e power minus a is going much faster. Of course, there's a constant, so I'm just for now ignoring the constant. All right. So I'm just saying that it goes to 0 at a much faster rate. So which of the two is a better bound? Which of the two goes to 0 faster?
Lower one.
Yeah, this goes far low faster because e power a minus a is going to 0 much faster. Okay, so even though Markov is giving a bad bound, okay, Markov is giving a bad bound, but we use that because it can be used in general for anything. You don't have to know that it was exponential to start with. You could have used this for any positive random variable. Okay, so that is the benefit of using the Markov. Okay, so one example we saw. Let us now look at another example of using Chebyshev. So please ask me if there are any questions. You can feel free to ask. So let me move on. Okay, so now let's try to use Chebyshev. So for this, let us suppose let x be a normal distribution. Okay, normal distribution. So normal random variable, I mean to say. Okay, so let me, if that confuses you, so let me say a normal random variable with mean, mu, and variance sigma squared. All right. So let's try to apply our Chebyshev. So let's take this probability. Probability that x minus mu is greater than sigma. Okay, so I'm asking basically, what is the probability that you will this? So let me draw this. So you have this normal distribution, something like this, right? Okay, so this is mean mu. Okay, so then this is mu minus sigma. Okay, mu plus sigma. What I'm asking is, I'm asking for the shaded probability, right? That is what this says. So this one we know from Chebyshev's, this is going to be less than or equal to variance of x divided by, so whatever the term here, okay, so it's square. Okay, now what does that give us? So this is equal to 1, right? Because variance of x is also sigma squared. So this gives us 1. Now we have learned. So what is this probability? Let us use knowledge that x is normal. So if you use that knowledge, what can you say about this probability? Somebody?
By z score, it will be inside will be 66.3 something of that sort, and outside will be the remaining.
Yes,
30.
very good. So you remember the 68, 95, 99.7. Actually, I might have told 99 rule in the class, but actually, if you want to do it more precisely, it is 99.7. But any case, the point is not that. This is what this, according to that rule, we know that x minus mu greater than sigma is equal to 1 minus probability that x minus mu is less than or equal to sigma. Okay, so this is the probability that you will fall one standard deviation within mu. Okay, and that is 68%. So this will be my 0. So yeah, it will be this. So this will be 0.32. Okay, so which is a better bound?
Lower one.
Lower one, because you are getting a better control on the tail probability. In fact, this for this bound I didn't need to use anything. Why is that? I didn't need to.
Less than 1.
Yeah, probability is always less than or equal to 1. Correct. So that itself is a by definition that is true. So there is nothing that is happening here. All right. So let us try to apply this once again and see what happens. Okay. So we saw for one standard deviation. Let us try to do it for two standard deviation and see whether it does anything better. Okay, so now we know that this is going to be less than variance of x divided by 2 sigma whole squared, which is 4 sigma squared. So that is equal to 1 over 4, which is 0.25. Okay, if I use the knowledge of normal, what do I get? Let's do that. X minus mu greater than 2 sigma is equal to 1 minus probability x minus mu is less than 2 sigma. All right, so this is going to be 0.95. So this is 1 minus 0.95. So this is again 0.05. Okay, so it's not going to get any better. So this second thing is this one uses the fact that x is normal. So similarly, let's try to even do the other case just to see. So x minus mu okay, is greater than or equal to 3 sigma. Okay, so this is going to be less than or equal to variance of x sigma squared divided by 9 sigma squared, which is equal to 1 over 9, which is 0.1111. Okay, if I use the knowledge that it was this one, this is actually going to be x minus mu greater than 3 sigma is going to be 1 minus 0.997. Okay, it's going to be 0.003. Okay, so you can see that whenever you use the knowledge that certain random variable is normal, you get better bounds. Okay, is that clear? Using x is normal gives better bounds. So that is clear. Better bounds in comparison to Chebyshev, in comparison to Markov. Okay, I hope this idea is clear to everybody. Okay, so these things are fine. So why is it that are we studying these things which seem to be not so useful, right? But actually it turns out the field of probabilistic inequalities is very useful because it does not require you to know what shape the random variable is taking. Okay, in life, when you look at various measurements, you may not exactly know what type of shapes it will take, right? So, but you need to be able to make conclusions. So that is why these inequalities, Markov and Chebyshev is useful. Actually, this is a very vast field. In fact, there is a textbook which is called Probabilistic Inequalities, which is like 500-page long. Okay, people have worked with different assumptions and got different inequalities. So this is an important field. Okay, and it is used to solve very important problems in machine learning. There is the next sequence of in this series is called as Chernoff bounds. Chernoff's bounds. Also, there is one more thing called as Hoeffding's inequality. These are all very useful in machine learning. There are algorithms which are called as multi-arm banded, okay, which uses these ideas. Okay, multi-arm bandit is in fact used in many companies to do things like product placement. So when you visit, you know, Flipkart or Amazon, okay, you see that every person has different things shown to them. The reason is they are doing some kind of customizing. They want to show you things which you are likely to buy, right? See, they have tens and thousands, 10,000s of products. Okay, they cannot show you all of that in one screen. Okay, some products you may buy, but they may be very cheap, which will not give them any revenue. Okay, so in order to learn what choice of algorithms, what choice of products are best for a certain customer, what they use is an algorithm called as multi-arm bandit. And what that uses internally is what is called as Hofting bound. Based on that, there is an algorithm called as multi-arm bandit. That's what is used. Okay, this is a very popular algorithm, very easy algorithm, which you will probably learn sometime. And there is where these inequalities are used. Okay, so I will try to give you a simple application going down the line, but not immediately. Perhaps in this class we may reach at some thing like that, but let's see. Okay, so yeah, so let's talk about the next thing. Okay, so now suppose you have a suppose we have a fair coin. Okay, so what that means, probability of getting ahead is 0.5. Okay, and let me ask this question. If I do basically and yeah, so let's say, let me do 10 tosses. Let us do 10 tosses. Okay, and I will do basically a computation called M10, okay, which is going to do x1 plus x2 plus x3 plus x10 divided by 10. So what am I doing here? So basically what I'm doing here is x1 is the first toss, outcome of the first toss. Okay, x2 is the outcome of the second toss, and so on. Okay, so I'm creating a new random variable M10, which is sum of all these tosses divided by 10. Okay, now I will, so this is an estimate of what? What am I trying to estimate here? Yes, anybody?
Weighted mean.
M10. Yeah, I'm trying to find out, not the mean is right, but I'm trying to find out what is the bias of the coin, right? So the coin, I have done some tosses. I want to know whether what is the probability that it gives an head. So that's what this is trying to do.
Sir,
Okay.
but we are aware of the bias, right?
No, this is, we are aware of the bias in this case, but suppose I didn't know.
Oh,
So
okay,
this was
sir.
not known. Yeah. So then if I do this, I will be able to get some estimate. Okay. So now coming back to the case where we do know, let me ask you this question. What is the probability that my estimate lies between 0.4 and 0.6? So what's the probability that M10 lies between this? Can someone tell me this? How do we compute this? So let us not try to use the inequalities immediately. That is for later. But if I were to give you in this exam, let's say I give you this question in exam, how will you do this? So I say don't use probabilistic inequalities. Just try to tell me what this probability is. How do you compute this?
So probability of M10 less than 0.6 minus probability of M10 less than 0.4.
Probability of M10 less than 0.6, and yeah. So, but how do we get this? How do we start computing this number?
So it's equal to the probability of getting 4, 5, or 6 heads among 10 tosses.
Exactly. And that is, what is that random variable?
4C10
Yeah,
into
that is a binomial. Exactly.
plus.
That's a
Yes.
binomial. So what this is, as he rightly pointed out, this is from the chance that you get 4 to 6, right? See, this probability M10 will be between 0.4 to 0.6 only when the numerator sums is ranging from 4 to 6, which means in 10 tosses, you got either 4 toss or 5 heads or 6 heads. Only in that case, M10 will be lying in this. And those things, like number of successes in 10 tosses, we know that is a binomial. Okay, so this will be n choose I, half to the power of I into half to the power of n is 10, right? So let me write that 10 minus I. Okay, so whatever this number, it can actually, if you do this, I have done this. I mean, I'm seeing this here. This is actually 0.65, 6563. Okay, you can trust me. You can go back and do this later. But yeah, I hope this is idea is clear. So what I'm trying to say is that, you know, if you are doing a coin toss with a fair coin, okay, even though you know it is fair, if you just try to estimate its mean, it's not going to be perfect, but it will be within the actual mean. It will be lying there, right? This is what this you have seen. The shape of binomial I had asked you in assignment, right? So it has this, it peaks around the true mean. So 0.5, around that there will be a biggest peak. And then, you know, you will have something like this. And then it decreases. Even in the exam, I asked you this question, right? So all of you know this. This is the histogram. But if I draw the PMF, it will be like this, right? So it has this shape, something like this. Okay, and the true thing will be around the actual mean. So this we know. Now let us do something else. Instead of doing 10 tosses, let us do 100 tosses. Okay, and let us do the same experiment. So what we are going to say is 0.4 less than or equal to M100 less than or equal to, yeah. So when I do this for 100 tosses, okay, everything remains the same. What happens when I'm doing 100 tosses? If my number is between 0.4 and 0.6, you are having, like what you're saying is 40 to 60 things, right? Your tosses, the number of heads you are getting is somewhere between 40 and 60. Okay, and everything else is the roughly similar. Okay, so let me ask the class, what do you think this number will be? Will it be higher than 0.6563 or will it be less than 0.6563? What do you think? Or will it be same?
Less than
Less
this.
than.
So what you're saying, this will be something like 0.65. What is the reason why you feel less?
Oh no, it will be greater.
Yeah, it will be
It will
greater.
be greater than.
It will be greater, is it? So can someone say why it will be greater? Can you tell me why it would be greater?
As
Because yeah, go ahead, go ahead.
as the number of test cases increase, the accuracy of the like uh, the the total probability to be around the mean increases.
So
Yeah,
it's
more
not,
number of
yeah, I mean,
coin tosses within your coin.
you have seen this in the assignment simulations that I gave you. You have seen this. So you're saying based on that, which is correct. Okay, and you can theoretically also show this. Actually, this number is 0.9648.
Sir,
Yeah.
won't it go closer to 0.5 as the number of experiments increase? Like,
Yes, it will grow to closer to 0.5. But what I'm asking is, what is the probability that your estimate is between
okay, sir. Yeah, sorry.
yeah. It will go closer to 0.5, but I am keeping my estimate around a interval. Okay, so let me write that. That's a good question that you asked, because so you know there is an interval which is 0.4 to 0.6. Okay, the same interval I'm taking for both these cases, and I'm asking what is the probability that my estimate falls in it. That's all. Okay. Okay, so this is good. So now we can do
Sir,
this. Yeah.
Can we also argue that if we like plot the variance of of this whole experiment, the
Yeah.
part which lies beyond these like beyond these brackets,
Yes.
that
Yes.
can, yeah, okay, sir.
Yeah, you can do that. I'm actually going there. Good. Okay, so that's what I'm going to talk about. So basically what we saw that if you fix a interval, okay, if you fix a interval around the mean, so the mean is here, I fix an interval around the mean. And what I argued is that more and more mass starts falling within this if you have more and more samples, more and more repetitions. All right. But outside this thing, it will go to zero. It will become smaller and smaller, right? Whatever lies outside will go smaller and smaller. And that is what is called as the weak law of large numbers, which is what I'm going to talk about now. Okay, so what I did for this interval, right? So probability that m 100 minus mu is greater than 0.1, okay, is going to be 1 minus 0.9648. That's what it is, right? So so mu was 0.5, okay. So I'm saying m100 minus mu, whatever the estimate is. So this thing, okay, saying that the estimate falls outside this is same as saying that this is happening. So let me repeat. The fact that m100 does not belong to 0.4, 0.6 is same as saying that m100 minus mu, okay, is greater than 0.1. Is that all right? Does everybody see this? Yeah.
Yes, sir.
Let me just
Sir,
yeah, go ahead.
can we say this law as it is also a form of central tendency or something?
Central tendency. So there is yeah, so everything will be lying closer and closer to the center, to the mean. That's correct.
Sir,
Yeah, you
so
can become.
sir, actually, I want to know that can we say this law as a central tendency, or there will be some difference between the central tendency and this law, weak law of large number?
I don't know what exactly you mean by central tendency. Yeah, who is that? What was the question again? Can you repeat?
Sir, actually, I want to know that this law. Actually, you told that that weak law. Those terms can we say as at the central?
No, I have not. I have
central
not yet explained the weak law. I'm coming there. Okay, so all I'm saying is we will go there talking about the weak law. Yet we haven't reached there. Okay, what I'm saying is, so whatever I think Siddhant was the one who said that if you look at the fact that your estimate is close to the mean in some interval, you can look at the other way around. You can talk about what is the estimate lying outside this, and then you can talk about if that goes to zero, if that becomes smaller and smaller when you do more and more experiments. Is that correct way to argue? He asked. And I said, yes, that's what we are going to do. But I didn't still explain what is weak law. I'm going to come there. But you just wait till that point and see whether that answers your question. All right. So we will come there. But so far, what I have told is that I have taken basically a fair coin, and I tried to find the probability of getting a head using 10 experiments and using 100 experiments. And what we have shown is the number for the same interval, you get better accuracy if you do more samples. That's what we have seen. Okay, and the error, this is the error, right? So the error that you are falling away from mu, okay, if you are falling away from mu, that is what this is saying. This is the error. This error tends to go to zero. That's what we have said so far. Okay, I have not yet specified the weak law, but let's get there. So, but before doing that, we should actually do something else. So after that, we will be ready to state and prove the weak law. All right. So let me get there, and then you can ask your question that time, Rishabh. Is that all right?
Okay, sir.
So before that, let me just ask the class. Is there any question till this? Is everything clear till whatever I have discussed here? Yes, can I have a quick poll? Okay, very good. So this is easy, right? I mean, I hope you don't find it too complicated. Okay, very good.
So,
Yeah.
so when we were discussing the inequalities, we were getting the more accurate answer when we were considering the fact that it was a normal distribution.
Yeah.
So like, why did we like use the inequalities then?
So normal distribution, when you use more and more information, you get better and better estimates, right? So if you knew it was normal, you know it exactly what is the probability that certain thing happens. You know it exactly. Okay. The problem in real situations is you don't know what's the distribution, right? So that is why we can't use what the shape of the distribution, because we don't know what shape it is, right? So for that purpose, we have these general laws, which is Markov and Chebyshev.
Oh,
Does that answer your question?
yes, yes.
Yeah. So you will see that something good happens as we will go more and more into this topic. You will see that there are some nice things that are happening. All right, but before that, let's do this. Okay. So now we have already seen let us look at, we know what is a sample mean, right? So we did that. So I didn't call it a sample mean, but this was what it was. Right? This is basically, if I want to estimate the sample, what is the mean of a distribution X. So X is a random variable. Okay, so this is a random variable and I want to estimate its mean. What I do is I will like draw independent, okay, and identical samples. Okay, so what that means is this is also called identical samples or identical distribution. Okay, so x1, x2, x3, xn, all of them are having the same shape. They are actually X itself. Okay, they are different instances of X. Okay, they are independent and identical. So this is also called as IID, independent and identical samples. Okay. So now what I would like to do is basically compute expected value of Mn. Okay, and then variance of Mn. Siddhant, you were also saying something like this, right? Try to find the expectation and variance. So yeah, this is where we are going. So now trying to use the knowledge that we have for Mn, let's write that. See, these things are not difficult. You may feel like something magical might be happening if you don't understand these things, if you don't remember these things, but it shouldn't be. So if some things are not clear, you just ask me. Okay, so this is what is Mn, right? So I'm just trying to find this. So now what is this going to be? So this is, now we are using linearity of expectations. So this is going to be, so 1 over n is a constant. We can pull that out. And then we can write this as, is everybody comfortable with this step? Any confusion till here? And now we know that x1, x2, x3, in the first case when we did the coin toss, we know that they are the probability of the expectation remains the same, which is p. But in general, when you are doing like from some other general distribution x, if you are drawing samples, exi for each of them will be equal to what? Yes. What is EXI?
Sir, shouldn't the summation be inside of E?
Summation will be inside of E, that is right. So the summation first will be inside of E, but what I'm doing next is like 1 over n I'm taking out, and then I have basically 1 over n expectation of summation. Is that right? This is okay? Are you okay with this?
Yes, sir.
And then I'm going to use that linearity of expectation, right? If you remember, E of x plus y was Ex plus Ey, right? Do you remember this?
Okay, sir.
Yeah, so basically, see what I'm trying to get at is that x is a random variable, okay, out of which you have drawn n samples. Okay, let us say the x is distribute the mean of x, e of x was mu, variance of x was sigma squared. Okay, but I don't know mu, right? Someone was saying that suppose, but we already know mu, but that's not the case. We don't know mu. We are there for that purpose. We are trying to find out the the mean mu by doing sample mean. Okay, I'm taking n samples and taking by n, and I get this. So my question is, what is E of xi? Yes, anybody?
It will be mu, right? For
Yeah, it will
all
be
I.
mu. Yeah, all of them will be mu because they are all essentially samples from X. Though you may not know what exactly that is. Okay, you can write it as mu. You don't know what exactly the value it takes, but we know that each of them will be mu. All right, so this will be 1 over n into mu plus n of them. So n mu. Okay, so this will be equal to mu. So basically what this is saying, if you do the experiment of drawing a number of samples and trying to estimate the mean using the sample mean, something like this, you are going to get mean which is equal to mu. All right. So that is good. That is what you expect to happen and it happens. All right. So let's try to do variance. We will do the same thing. So it will be variance of x1 plus x2 plus x3 plus xn divided by n, right? So 1 over n is like a constant. We will pull that out. It will be 1 over n square variance of x1 plus x2 plus x3 plus xn. Okay, so this much I think is clear for everybody. But now whenever I'm drawing samples, I said we will draw samples which are independent. So samples are independent, right? When you do a coin toss, the first coin toss has no role on the second coin toss, right? If you think of IPL, I'm doing the first coin toss. Second coin toss does not depend on what was the outcome of the first coin toss. Similarly, fifth coin toss does not depend on what was the first, second, third, or fourth. They are all independent samples. And when you have independence and when you take the variance of sum of independent random variables, it becomes, yes, what does it become?
N into variance of x.
Yes, so this becomes sum of variances. Okay. And what is variance of xi?
Sigma square.
Yeah, so this is going to be sigma squared plus sigma squared n of them. So n sigma squared. So essentially, if you do, you will get this as sigma squared by n. So expected value of mn is mu. Variance of mn is sigma squared by n. Okay, so this is something that we can see by this algebra that we did. And now we can talk about what we were interested in, right? So what were we interested in? So we were interested in the tail probability. So probability that our estimate mn minus mu is greater than some 0.1 was something that I took in the example. But if I take some random number, let's say epsilon. Okay, so this is called as epsilon, epsilon actually, epsilon, Greek letter. Okay. So this is what we are interested in, right? So my estimate is whatever I'm estimating is away. There is an error. So this is like an error. So this whole thing, you can think of probability of error, right? If my estimates were correct, and if epsilon is a number greater than 0, okay, very small number, okay, so if my whole process was correct, I should be within epsilon, not outside of epsilon. Okay, if I'm outside of epsilon, that is error. Now what is this? Now we can use what we know best. If this is going to be less than or equal to, I'm using Chebyshev. So am I audible now?
Yes, sir.
Yes,
So
sir.
something happened in my Wi-Fi. So let me come back to this. So I sorry about that. Okay, so what I was saying is that yeah. So this is where we kind of got. So the error can be bounded by the Chebyshev's thing. So this is
So
going to
your
be.
screen is not presented.
It's not presented. Okay, just hold on. Okay, it's going to be coming soon. How about now?
Yes, sir.
All right. So yeah, so basically what we were trying to do is like we are doing some kind of a estimate for the sample mean. Okay, think of it, this situation, what is coming in. If you don't know, if you don't know the sample mean itself, you don't know, but you want to know if I do enough number of samples, will it give me the correct mean, right? So this is what we are getting at. So this is what we will get. This is using Chebyshev. Okay, and what is this equal to? This is going to be equal to variance of Mn is sigma squared by n. Okay, so what we have in fact shown is that probability that your error, okay, is going to 0, because as n tends to infinity, this tends to 0. So what we get is we get for all epsilon greater than 0, right? Because this does not depend on epsilon. As long as epsilon is greater than 0, we are fine. What we get, probability that Mn minus mu, okay, this error, okay, is going to 0. So basically what that says in terms of mathematics, if you want to write this, limit as n tends to infinity, probability that Mn minus mu, basically the error probability goes to 0, is 0 actually. Okay, so whenever this event happens, what we are saying is that Mn converges in probability, we write like this, to mu. Okay, and so basically what it says is you are going to get better and better estimate of your mu as n tends to infinity. Okay, this is called as the weak law of large numbers. Okay, there is something called as a strong law, but that is called as a concept called as almost sure Hello, am I audible?
Yes, sir.
Sorry about
Yes,
that. There
sir.
is some network
sir.
issues. So let me just conclude. What I'm saying is that your sample mean, the estimates that you're going to get is going to converge to mu. You're going to get mu. Okay, so that is all I wanted to say. This is called as a weak law. So are there any questions so far? Is everything okay? All right, so let me stop here. There seems to be some network problem that is happening. So anyway, so I will stop here. I will upload this in YouTube. So, okay, have a good lunch. Thank you, everybody.